The ocean floor is not a quiet graveyard of sand and silence, but a living, breathing skin that constantly renews itself in the dark. We often imagine the bottom of the sea as a place of stillness, a vast and featureless plain where dust settles over millions of years, undisturbed by the chaos of the world above. But this is an illusion born of distance. If we could drain the oceans, we would not see a flat, grey expanse. We would see a landscape more violent and majestic than any continent on Earth. We would see thousands of chimneys puffing black smoke into the void, mountains that dwarf Everest rising from the abyss, and rivers of molten rock glowing red against the crushing blackness of the deep. The ocean floor is alive with fire. Most of the volcanic activity on our planet does not happen on land, where we can see it, but deep underwater, hidden by miles of crushing pressure. Scientists estimate that nearly 80% of all volcanic eruptions on Earth occur beneath the waves. This means that the image we have of a volcano, a conical mountain puffing ash into a blue sky, is actually the exception, not the rule. The true face of Earth's volcanism is dark, wet, and incredibly deep. It is a silent fire that burns without oxygen, shaping the crust of our world in a process that has continued uninterrupted for billions of years. These submarine volcanoes are so numerous that we have not even counted them all. While there are about 1,500 active volcanoes on land, estimates for underwater volcanoes range into the millions. Most of these are extinct, silent monuments to ancient eruptions, but tens of thousands are active right now. They are erupting at this very moment, pouring fresh lava onto the seafloor while we sleep, while we work, and while we watch the calm surface of the ocean, completely unaware of the churning creation happening below. The pressure at these depths changes the very nature of the explosion. On land, a volcanic eruption is a loud, chaotic event. Gas expands rapidly, blasting rock into dust and sending shockwaves through the air. But deep underwater, the weight of the ocean is so immense that it acts like a heavy lid. At a depth of 2,000 meters, the pressure is over 200 times greater than atmospheric pressure. This crushing force suppresses the expansion of gases. It keeps the explosion contained. Instead of a violent, towering plume of ash, underwater eruptions often behave more like a leaking pipe or a slow, oozing wound in the planet's skin. The lava squeezes out in heavy, bulbous shapes, rolling over itself in a slow-motion landslide of fire. This unique environment creates rock formations that exist nowhere else. When molten rock, which can be over 1,000 degrees Celsius, meets seawater that is barely above freezing, the reaction is instantaneous. The outer skin of the lava cools in a fraction of a second, turning into obsidian-like glass, but the inside is still liquid, hot, and pushing forward. This internal pressure cracks the fresh glass, and a new bulb of lava squeezes out, only to freeze instantly in the cold water. This process repeats over and over, creating piles of rounded stone pillows that look like toothpaste squeezed from a giant tube. Geologists call this pillow lava, and it is the most common rock on the surface of our planet, paving the floors of all the world's oceans. Yet few human eyes have ever seen it form. The cooling power of water is far greater than air, which means underwater volcanoes lose their heat with terrifying speed. A lava flow on land might take weeks or years to cool down completely. In the deep ocean, the heat is ripped away so fast that the lava can shatter. The thermal shock is so intense that the rock essentially explodes from the rapid change in temperature, turning into a fine sand of glass shards. This grit settles on the ocean floor, creating vast fields of black, glassy sand that crunch under the treads of robotic explorers. Despite this rapid cooling, the sheer amount of heat released by these volcanoes is staggering. It is enough to alter the currents of the ocean itself. When a major eruption occurs, it creates a plume of superheated water called a megaplume. These massive columns of hot water can rise thousands of meters from the seafloor, carrying chemicals and minerals toward the surface. They can be tens of kilometers wide, spinning like underwater tornadoes. These plumes act as elevators for the deep ocean, mixing the cold, stagnant bottom water with the layers above and distributing the heat of the Earth's core into the global ocean system. It is strange to think that the freezing depths of the ocean are warmed by the same fire that burns in the center of the Earth. In some places, the water near these volcanoes is so hot it should boil, but the pressure prevents it from turning into steam. It remains liquid, even at temperatures far above the boiling point we know on land. This superheated water becomes a potent solvent, dissolving metals and minerals from the surrounding rock as if they were sugar in hot tea. It becomes a toxic, metal-rich soup that would kill almost anything on the surface. Yet down there, it becomes the breath of life for a strange and alien ecosystem. We often speak of volcanoes as destructors, but in the ocean, they are the primary creators. The seafloor is constantly being born at these volcanic ridges. The Atlantic Ocean is getting wider every year, about the speed your fingernails grow, because underwater volcanoes in the middle of the ocean are pushing the continents apart. This is not a violent separation, but a slow, steady construction. New lava rises to fill the gap, cooling to form new crust. The ground you walk on, the continents we call home, are essentially rafts floating on a sea of denser rock that was forged in these underwater fires. The vast majority of Earth's crust was made this way. It is a factory floor that never shuts down. If you were to drain the oceans, you would see a winding mountain range running around the globe like the seam on a baseball. This is the global mid-ocean ridge system, the longest mountain chain on Earth, stretching for 65,000 kilometers. It is almost entirely volcanic, a massive scar where the planet is ripping itself open and healing itself at the same time. Along this ridge, the geology is raw and young. There is no dust here, no sediment, just sharp, black rock that was molten magma only yesterday or last year. It is a landscape of stark contrast, the deepest, darkest black rock against the palest white crabs and shrimp that scuttle across it. The darkness is absolute. Sunlight can only penetrate a few hundred meters into the ocean. By the time you reach the average depth of these volcanoes, you have been in total darkness for miles. The only light comes from the glow of the lava itself, a dull, sinister red that fades quickly into the gloom. Sometimes, this deep fire grows tall enough to touch the sky. This is how islands are born. Every island in Hawaii, every atoll in the Pacific, began as a humble eruption on the seafloor, miles below the surface. It started as a pile of pillow lava, growing inch by inch, eruption by eruption, in the crushing dark. It takes hundreds of thousands, sometimes millions of years, for a seamount to build itself up from the abyss. It is a lonely, quiet struggle against the weight of the ocean. For eons, the volcano grows in secret. It builds a broad, gentle slope, layering flow upon flow. It is only when it nears the surface that the character of the volcano changes. As the pressure of the water decreases, the gases in the magma can finally expand. The eruptions become explosive. The peaceful oozing of pillow lava turns into violent blasts of steam and ash. When the hot lava hits the shallow water, it flashes to steam instantly, blowing the rock apart. This is the most dangerous phase of an island's life, the Surtsean eruption, named after the island of Surtsey, which rose from the sea off the coast of Iceland in 1963. Witnesses to the birth of Surtsey saw the ocean boiling. Enormous jets of black ash and steam shot miles into the air, piercing the clouds. Lightning flickered within the ash plumes, generated by the static of colliding particles. The sea glowed with the heat of the birth. It was a violent, chaotic war between fire and water, and for a long time, it looked like the water would win. The waves washed away the loose ash as fast as the volcano could produce it. It was only when the lava began to flow, capping the loose ash with hard, erosion-resistant rock, that the island could survive. Today, Surtsey is a quiet, grassy place, home to seals and seabirds. But its foundation is a testament to that underwater battle. This process has happened countless times over Earth's history. The Emperor Seamounts, a chain of underwater mountains stretching from Hawaii to Russia, are the drowned ancestors of the Hawaiian Islands. Millions of years ago, they were tall volcanic islands, basking in the sun. But as the Pacific tectonic plate moved them away from the volcanic hotspot that created them, their fires went out. Without the constant supply of new lava, the ocean began to reclaim them. Wind and waves eroded their peaks, and the cooling crust beneath them slowly sank. Now, they are ghosts, flat-topped mountains, hidden thousands of meters beneath the waves, their beaches and coral reefs preserved in the cold dark. These sunken islands, called guyots, are flat on top because they were once shaved smooth by the waves. They are like tables waiting for a dinner party that will never come. They stand as silent markers of where the shoreline used to be. Exploring them is like walking through a frozen moment in time. You can find fossilized coral reefs and ancient beach pebbles deep in the abyss, remnants of a time when these peaks felt the warmth of the tropical sun. The sheer scale of these underwater mountains is hard to comprehend. Mauna Kea in Hawaii is often cited as the tallest mountain on Earth if measured from its base on the seafloor. It rises over 10,000 meters from the abyss, far taller than Everest. But Mauna Kea is just one example. There are seamounts in the Pacific that are so massive, their gravity actually pulls water toward them, creating a permanent bump on the ocean's surface that can be detected by satellites. These are mountains that create their own tides, their own currents, and their own weather systems underwater. When ocean currents hit these massive underwater walls, they are forced upward. This upwelling brings nutrient-rich cold water from the deep up toward the sunlit surface. This creates an explosion of life. The waters around seamounts are often teeming with fish, sharks, and whales. They are oases in the blue desert of the open ocean. The volcano, even if it has been extinct for millions of years, continues to feed the ocean by its mere presence, guiding the flow of water and nutrients like a giant, silent shepherd. But let us return to the active ridges, where the Earth is splitting apart. The mid-ocean ridge system is a place of constant, slow-motion change. It is not a single line, but a fractured, jagged zipper. The ridge is broken into segments, offset by transform faults, where huge sections of the crust slide past each other. These faults can be hundreds of kilometers long, creating steep cliffs and deep canyons on the ocean floor. It is a chaotic, rugged terrain that makes the Alps look smooth by comparison. Deep in these rift valleys, the water pressure is crushing. It would squeeze a styrofoam cup into the size of a thimble. Yet, the water here is not stagnant. It is circulating through the rocks. The ocean floor is cracked and fissured, and cold seawater seeps down into these cracks. It travels kilometers deep into the crust, getting closer and closer to the magma chamber below. As it descends, it heats up, it expands, it becomes buoyant, and then, like a pressure cooker, it shoots back up toward the surface. This is the engine that drives the famous hydrothermal vents. These are not volcanoes in the traditional sense, as they do not spew lava. Instead, they spew hot, chemical-rich water. When this superheated fluid, which can be 300 or 400 degrees Celsius, hits the freezing bottom water, the minerals dissolved in it precipitate out instantly. They turn into dark, billowing clouds of particles that look exactly like smoke. This is why they are called black smokers. The minerals that settle out of this smoke are building blocks. They accumulate around the vent opening, building tall, hollow chimneys. Some of these chimneys can grow to be tens of meters high, towering like Gothic spires in the darkness. They are fragile, made of sulfides and iron, and they can grow incredibly fast, sometimes 30 centimeters a day. A chimney can rise from nothing to the height of a 2-story house in less than a year. They are temporary cathedrals, constantly collapsing and rebuilding themselves in the dark. The water that comes out of these vents is strange stuff. It is acidic, often with the pH of vinegar or lemon juice. It is loaded with hydrogen sulfide, the chemical that smells like rotten eggs. To us, it is toxic waste, but to the deep ocean, it is a buffet. This fluid carries the chemical energy needed to sustain life without sunlight. It is a different kind of fire, a chemical fire that burns in the cold water. Scientists were shocked when they first discovered these vents in 1977. They expected a barren desert. Instead, they found bustling cities of life. The chimneys were covered in carpets of bacteria, white and orange and red mats that shimmered in the submersible's lights. Crawling over these mats were blind shrimp, giant white crabs, and clams the size of dinner plates. And rising from the rocks were tubes, giant tube worms, 2 meters long, with bright red plumes that swayed in the hot, toxic water. These tube worms have no mouths and no stomachs. They do not eat in the way we understand eating. Inside their bodies, they hold billions of symbiotic bacteria. The worm absorbs the toxic hydrogen sulfide from the water and feeds it to the bacteria. The bacteria, in turn, use the chemical energy to produce sugar, which feeds the worm. It is a perfect partnership, a biological solar panel that runs on poison instead of light. These creatures are aliens on their own planet, thriving in conditions that would kill almost every other animal on Earth. The discovery of these ecosystems changed our understanding of biology forever. Before this, we believed that all life on Earth ultimately depended on the sun. Plants use sunlight to make food, animals eat the plants, and so on. But here, in the black abyss, was a food web that was completely independent of the sun. It was powered entirely by the heat of that Earth. It proved that life is more resilient, more adaptable, and more stubborn than we ever imagined. It suggested that life could exist on other worlds, on moons far from the sun, huddled around similar volcanic vents in dark, icy oceans. The environment around a vent is one of extreme contrasts. The water coming out of the chimney can be hot enough to melt lead, while just a few centimeters away, the water is near freezing. The animals that live here must navigate this thermal minefield. The Pompeii worm, for instance, lives with its tail inside a tube where the water is 80 degrees Celsius, while its head sticks out into water that is 20 degrees. It is the most heat-tolerant animal known to science, living constantly on the edge of being cooked, protected by a fleece of bacteria on its back that insulates it from the heat. These vent fields are ephemeral. The plumbing of the volcano changes. An earthquake shifts the rocks, a lava flow covers a vent, or the heat source simply moves. When the hot water stops flowing, the city dies. The worms starve, the clams perish, and the chimneys slowly crumble into rust. But life in the deep is a traveler. The larvae of these creatures drift through the endless dark, riding the deep ocean currents for weeks or months, waiting to sniff out the chemical trace of a new vent. They are nomads of the abyss, drifting from oasis to oasis in a desert of cold. There are not just black smokers, there are also white smokers. These vents release cooler water, usually rich in barium, calcium, and silicon. The minerals they build are white, creating ghostly, pale chimneys that look like giant wax candles or stalagmites in a cave. The chemistry here is different, more alkaline. Some scientists believe that these alkaline vents, specifically a type discovered at a place called the Lost City in the Atlantic, might be the place where life on Earth first began. The microscopic pores in the rock chimneys could have acted as the first cell walls, trapping chemicals and encouraging the complex reactions that eventually led to the first living spark. The Lost City is a haunting place. It sits on top of a massive mountain called the Atlantis Massif. The spires here are made of limestone, not metal sulfides. They can be 60 meters tall, glowing ghostly white in the lights of a submarine. They look like ancient ruins, a sunken metropolis of jagged towers. The water that seeps from them is not powered by magma, but by a chemical reaction between the seawater and the mantle rock itself. It is a silent, flameless heat that has been running for hundreds of thousands of years, much longer than the violent, short-lived black smokers. The ocean is a layered world, and underwater volcanoes disrupt these layers. The heat they release creates shimmer in the water, a mirage in the deep. This shimmering water is often the first sign that a vent is nearby. Pilots of deep-sea submersibles look for this refractive index anomaly, a wavering of the view that tells them the water temperature is changing. It is like seeing heat waves rising off hot asphalt on a summer day, but happening in pitch blackness under 6,000 pounds of pressure per square inch. But sound travels differently here too. Water is an excellent conductor of sound, far better than air. A volcanic eruption underwater sends acoustic waves rippling through the ocean for thousands of miles. These are not sounds we could hear with our ears. They are often low-frequency rumbles, deep vibrations that travel through the density of the water. Hydrophones, the underwater microphones, pick up these sounds. They hear the cracking of rock, the hiss of escaping gas, and the dull thud of lava pillows tumbling down a slope. Sometimes, the ocean sings with the voice of the volcano. In 1997, researchers detected a sound that was incredibly loud, ultra-low frequency, and organic in nature. They called it the bloop. For years, people speculated it was a giant animal, a sea monster of legend. But eventually, the evidence pointed to something geologic, likely a massive cracking of an iceberg or an underwater quake. However, volcanoes have their own signature sounds. A submarine eruption can sound like a freight train, or like bubble wrap being popped, or sometimes like a choir of moans and groans as the earth stretches and breaks. Scientists listen to these sounds to monitor the heartbeat of the planet. By placing hydrophones in the SOFAR channel, a layer of water that acts like a sound tunnel, they can hear small eruptions halfway across the globe. A small burst of lava near Guam can be heard by listening stations off the coast of Washington state. The ocean is a whispering gallery, carrying the secrets of its geology to anyone with the ears to listen. The pressure waves from these eruptions can be deadly if you are too close. The shock wave travels faster than the speed of sound in air. For the delicate creatures of the deep, a nearby eruption is a concussive event. But for the ocean itself, it is just a pulse. The water absorbs the energy, dampening the violence. A blast that would level a city on land might only create a thump and a cloud of bubbles at depth. The weight of the water acts as a blanket, muffling the rage of the earth. There is a special type of volcano that exists only in the deep ocean, called the petit spot volcano. These are tiny, young volcanoes that pop up on very old, cold oceanic crust. far away from any tectonic plate boundaries. They shouldn't be there. They are a geological mystery, small pimples of magma squeezing through cracks in the plate as it bends and flexes. They remind us that the Earth is not a rigid shell, but a flexible skin that can leak and bleed in unexpected places. The lava from these deep eruptions is not always the same. On land, we have red lava, but underwater, color behaves differently because light is absorbed by the water. Red is the first color to disappear. At the depth of most volcanoes, red light is completely gone. So, if you were to look at molten lava with your naked eye down there, it wouldn't look red. It would look glowing orange or yellow, appearing incredibly bright against the total blackness. But as it cools, it turns gray, then black. If you shine a flashlight on the hardened rocks, they might be coated in a rust-colored mat of iron-oxidizing bacteria, giving the landscape a bloody, bruised appearance. The deep ocean floor is also home to vast plains of asphalt volcanoes. Yes, asphalt. In the Gulf of Mexico, there are mounds on the seafloor that look like hardened lava, but they are actually made of tar. Oil and gas seep up from deep reservoirs, reacting with the seawater to form thick, sticky asphalt structures. They look like lilies made of black glass. These tar lilies are technically volcanoes of petroleum. They flow in slow motion, creating a landscape that is sticky, toxic, and strangely beautiful. Life has adapted here too, with tube worms and bacteria that feast on the oil, turning a pollution spill into a banquet. Even stranger are the mud volcanoes. These are not spewing lava, but cold, pressurized slurry of mud, water, and methane gas. They exist on the continental slopes, where sediments pile up thick and heavy. When the pressure gets too high, the trapped water and gas liquefy the mud and shoot it up to the surface. Some of these mud volcanoes are enormous, kilometers across. They burp methane bubbles into the water column. Sometimes, these bubbles are trapped in ice, a strange substance called methane clathrate. It looks like white sorbet or dirty snow, but if you bring it to the surface and light a match, the ice will burn. These clathrate fields are vast energy reserves, but also ticking time bombs. If the ocean warms up too much, the ice melts, releasing the methane. Methane is a powerful greenhouse gas. Some scientists believe that massive releases of methane from these underwater mud volcanoes have caused rapid climate change in Earth's past. It is a reminder that the ocean floor is not disconnected from the atmosphere. What happens in the dark, cold depths can change the weather in the bright, sunlit world above. The connectivity of the ocean is vast. The iron spewed out by hydrothermal vents doesn't just stay on the bottom, it drifts. Iron is a fertilizer for the ocean. In many parts of the sea, the surface water is full of nutrients, but lacks iron. When the plume from a deep volcano eventually rises and mixes, it delivers this missing ingredient. This can trigger massive blooms of plankton on the surface, thousands of miles away and years later. The microscopic plants bloom, sucking carbon dioxide out of the air. When they die, they sink, carrying that carbon back down to the deep. It is a planetary breathing cycle. The volcano exhales chemicals, the plankton inhale them, and the carbon is buried again in the sediment. This iron fertilization is a critical part of the Earth's climate system. Without the constant leakage of metals from underwater volcanoes, the oceans might be much less productive. The great fisheries of the world, the oxygen we breathe, much of it owes a debt to the dark, toxic smoke puffing out of the mid-ocean ridges. The fire below feeds the life above. We are only just beginning to map these hidden giants. We have better maps of the surface of Mars than we do of the ocean floor. Most underwater volcanoes are known only as blips on a sonar screen or anomalies in satellite gravity data. We know they are there, because they bend the water surface with their mass, but we have never seen them. Every time we send a ship to map a new section of the ridge, we find surprises. Valleys where we expected mountains, vents where we expected flat plains, new species where we expected barren rock. The largest volcanic feature on Earth is not Mauna Loa in Hawaii, as we used to think. It is arguably the Tamu Massif, a submarine plateau located about 1,000 miles east of Japan. It is extinct now, but its footprint is roughly the size of New Mexico. It is a single, massive mound of basalt that formed about 145 million years ago. It is comparable in size to Olympus Mons on Mars, the largest volcano in the solar system. For decades, we thought it was a collection of smaller volcanoes, but later analysis revealed it is one colossal beast. It sits quietly in the dark, a sleeping giant that hints at the incredible volcanic power the Earth was once capable of unleashing. Even deeper than Tamu Massif are the volcanoes of the Mariana Trench. The trench is the deepest scar on the planet, a subduction zone where one tectonic plate is diving under another. As the Pacific plate sinks into the mantle, it melts. This magma rises to form the Mariana Arc volcanoes. Some of these are islands, but many are submarine. The Champagne vent, found at the Aifuku volcano in the Marianas, spews liquid carbon dioxide. At this depth, 1,600 meters, the pressure is so high that CO2 exists as a liquid, not a gas. It bubbles out of the vents like droplets of oil in water, milky white and shimmering. It is a jacuzzi of pure acid, bubbling quietly in the absolute dark. This liquid carbon dioxide is cold, only about 4 degrees Celsius, but the vents nearby are hot. It is a thermal contradiction. Exploring these places requires robots that can withstand pressures that would crush a car into a marble. The remotely operated vehicles, or ROVs, are our eyes and hands. They descend on thin cables, beaming back high-definition video of a world that looks like a different planet. The lights of the ROV carve a tunnel of visibility through the eternal night. Inside that tunnel, we see colors that have never been seen before. The bright yellow of sulfur, the rusty red of iron, the iridescent glitter of pyrite or fool's gold settling on the flanks of a black smoker. The sound of the ROV thrusters is a high-pitched whine, foreign in this silent world. When the pilots turn off the lights to rest, the darkness is total. But it is not empty. Bioluminescence flickers in the water column. Tiny plankton flash blue when disturbed. Jellyfish drift by, pulsing with their own internal light. And down on the volcano itself, the heat glow is invisible to the eye, but visible to the infrared sensors. The rock is radiating energy. The transition from rock to water is blurry here. The water circulates through the porous crust like blood through tissue. There is a deep biosphere of microbes living inside the rocks themselves, hundreds of meters below the sea floor. They live in the tiny cracks, feeding on the chemical energy of the rock. Some scientists estimate that the mass of microbes living inside the Earth's crust is greater than the mass of all life on the surface combined. We walk on a planet that is alive not just on the skin, but deep within the muscle. These rock-dwelling bacteria reproduce incredibly slowly. Life in the deep lane is slow. Some of them may divide only once every 100 or 1,000 years. They are living on geological time, barely alive by our standards, but persisting for eons. They are the true natives of Earth, the original inhabitants who have been here since the planet cooled, hiding in the warm, wet rock while the surface world froze and burned and changed 1,000 times. Volcanoes also have a life cycle of destruction. They do not just build, they collapse. As a seamount grows, its sides become steep and unstable. The lava piles up loosely. Eventually, a massive section of the volcano can break off and slide into the deep. These submarine landslides are some of the largest mass movements of rock on Earth. Blocks of rock the size of cities can slide for dozens of miles across the seafloor. These landslides can generate massive tsunamis, silent waves that travel across the ocean before rearing up to strike distant shores. The evidence of these past collapses surrounds the Hawaiian Islands, huge debris fields of jumbled rock scattered across the deep ocean floor, monuments to the structural failure of mountains. But the ocean heals these wounds quickly. Sediment rains down, the marine snow. It is a ceaseless drift of dead plankton, dust, and fecal matter from the surface. It covers the sharp lava flows, softening the edges. It fills the cracks. Over millions of years, it buries the volcano in a thick blanket of grey ooze. The fire dies, the heat fades, and the seamount becomes a tomb. But beneath the sediment, the rock remains, a hard magnetic record of the Earth's polarity at the moment it froze. Every lava flow records the direction of north at the time it cooled. Because Earth's magnetic field flips every few 100,000 years, the seafloor is striped with magnetic bands, positive, negative, positive, negative. These stripes, hidden in the volcanic rock, were the key to unlocking the theory of plate tectonics. They are the planet's barcode. By reading them, we can rewind the movement of the continents. We can see how the Atlantic unzipped, how India raced north to crash into Asia, and how the floor of the Pacific has been recycled again and again. The history of the world is written in the frozen magma of the deep ocean. This recycling process occurs at the trenches. The old, cold volcanic crust, heavy with millions of years of sediment, eventually sinks back into the mantle. It dives down into the deep earth, carrying water and carbon with it. This water lowers the melting point of the rock, causing it to melt and rise again as new magma. It is the ultimate recycling loop. The water you drink may have once been trapped in a rock on the ocean floor, dragged down into the hellish heat of the mantle, and burped back out by a volcano millions of years later. The Earth wastes nothing. As we drift through these dark waters, imagine the pressure pressing against your chest, a hug from the ocean that never lets go. Imagine the cold, just a few degrees above freezing, preserving the ancient rocks. And imagine the heat, the sudden, violent pockets of boiling water that sustain life in the void. It is a world of extremes, balanced in a precarious harmony. A world where rock turns to liquid and water turns to stone-filled smoke. And this is just the beginning of the descent. We have touched the ridges and the vents, the birth of islands and the death of mountains. But there are deeper mysteries, stranger eruptions, and vastly more powerful forces waiting in the darkness below. The darkness here is not empty. It is a canvas for the strangest forms of life our planet has ever produced. In the crushing blackness surrounding these underwater volcanoes, biology has found a way to rewrite the rules of existence. We are used to life that craves the sun, to forests that reach for the light, and animals that roam the day. But down here, the sun is a myth. The only star these creatures know is the glowing heart of the volcano itself. They gather around the hydrothermal vents like travelers around a campfire in a frozen desert, drawing warmth and energy from the very thing that should kill them. Among the most iconic of these deep-sea residents are the giant tube worms. They stand like tall, white stalks of bamboo, tipped with magnificent, feathery plumes of bright red. These plumes act like gills, exchanging chemicals with the seawater. The red color comes from hemoglobin, the same molecule that makes our blood red. But in these worms, it is incredibly concentrated, designed to bind oxygen and hydrogen sulfide from the water. They have no eyes to see the dark, no mouths to eat, and no stomachs to digest. Instead, they are living greenhouses. Inside their bodies is a specialized organ called a trophosome, packed with billions of symbiotic bacteria. The worm harvests the toxic chemicals from the volcano and feeds them to the bacteria, and in return, the bacteria produce sugars that feed the worm. It is a relationship of perfect balance, allowing them to grow to heights of 2 meters or more, swaying gently in the currents of superheated water. Crawling among these worms are creatures that seem plucked from a fantasy. The Yeti crab, discovered only recently in the South Pacific, is a pale, blind crustacean covered in thick, silky white fur. This fur is not for warmth, for the ocean here is already a mix of freezing and boiling. The fur is a farm. The crab waves its hairy arms over the volcanic vents, encouraging bacteria to grow on the strands like crops in a field. When the bacteria are thick enough, the crab uses its mouthparts to comb its own fur, harvesting the microscopic food it has grown. It is a gardener in the abyss, tending to its livestock in the shadow of a smokestack. Even more armor-plated is the scaly-foot gastropod, a snail found only at specific vents in the Indian Ocean. It is the only animal on Earth known to incorporate iron into its skeleton. The snail builds a shell layered with iron sulfides, creating a natural suit of armor that is magnetic. If you were to hold a strong magnet near one, it would stick. Its foot is covered in hardened, metallic scales to protect it from the venomous darts of predatory cone snails and the pinching claws of crabs. It is a creature of the Iron Age, forging its own defense from the dissolved metals of the volcano's breath. The water around these vents is often swarming with shrimp, specifically a species known as Rimicaris exoculata. They move in chaotic clouds, thousands of them climbing over the chimneys and scraping bacteria from the rock. They have no eyes in the traditional sense, for there is nothing to see. Instead, they have a large, light-sensitive patch on their backs. This patch cannot form images, but it can detect the faint, ghostly glow of infrared radiation emitted by the hot vents. They see the heat. This allows them to hover dangerously close to the boiling water, close enough to feed, but far enough not to be cooked. They dance on the edge of thermal destruction, guided by a sense we can barely imagine. But the influence of these volcanoes extends beyond the immediate heat of the vents. In the quieter, cooler areas of the seafloor, we find cold seeps. These are places where hydrocarbon-rich fluids, often methane and brine, seep slowly out of the ocean floor. They do not build towering chimneys, but they create their own strange landscapes. One of the most surreal sights in the ocean is a brine pool. Because salt water is denser than fresh water, and extremely salty water is denser still, these pools form distinct underwater lakes. There are lakes on the bottom of the ocean, complete with shorelines, ripples, and even waves. A submarine descending to a brine pool looks like it is flying over a dark beach. The water of the pool is often a murky, toxic soup of methane and dissolved salts, so dense that a submarine can float on top of it. Mussels line the shores of these underwater lakes, feeding on the bacteria that thrive at the interface. If an unsuspecting fish or eel swims into the brine, it can go into toxic shock and die, preserved in the salty fluid, like a pickle in a jar. These pools are timeless traps, silent and deadly, fueled by the slow leakage of the Earth's chemical reserves. Life in these deep environments is not just about survival, it is about travel. The vents are temporary. A volcanic eruption can pave over a colony of tube worms in an instant. An earthquake can shut off the flow of hot water, starving the ecosystem. To survive, these species must be able to move. They do not move as adults, but as larvae. They release billions of microscopic offspring into the water column. these tiny travelers drift on the deep ocean currents, sometimes for hundreds of miles, in a state of suspended animation. They are waiting for a signal, a whiff of sulfide, a taste of iron, a change in temperature that tells them they have found a new home. This creates a paradox of isolation and connection. Each vent field is like an island in a vast desert, yet the species are genetically connected across entire oceans. They use the deep currents as highways, hopping from one volcanic stepping stone to the next. Some scientists believe that whale falls, the carcasses of dead whales that sink to the sea floor, act as intermediate stations. A whale carcass releases sulfur and oil as it decomposes, creating a temporary chemical environment similar to a vent. The larvae might settle there, grow, and reproduce for a few generations before their descendants move on to the next volcano. The death of a giant from the surface becomes a lifeline for the children of the deep fire. The darkness of these depths is occasionally broken by biological light. Bioluminescence is common in the deep sea, but around volcanoes, it takes on a different purpose. Predators use glowing lures to attract prey in the dark. Siphonophores, long gelatinous colonies of animals, drift like drift nets of light, stinging anything that touches them. The light is cold, blue or green, a stark contrast to the red heat of the lava. It is a silent language of flashes and pulses, signaling danger, attraction, or camouflage in a world where sunlight has never touched. Just as light behaves differently here, so does sound. The ocean is a dense medium, and sound travels through it nearly 5 times faster than it does through air. In the vast open spaces of the deep ocean, sound does not just fade away, it is channeled. There is a specific layer of the ocean, usually around 1,000 meters deep, known as the SOFAR channel, or the sound fixing and ranging channel. In this layer, the pressure and temperature interact to trap sound waves, preventing them from scattering toward the surface or the bottom. It acts like a global fiber optic cable for noise. A sound generated in this channel can travel for thousands of miles without losing much energy. Whales have known this for millions of years, using it to sing to each other across entire ocean basins. But the channel also carries the voice of the Earth. When a submarine volcano erupts, the sound enters this channel and races across the globe. A rumble in the South Pacific can be picked up by hydrophones in the North Atlantic. The ocean is constantly murmuring with the sounds of shifting plates, cracking crust, and bubbling gas. This acoustic landscape is how we discovered many of these volcanoes in the first place. During the Cold War, the military set up vast networks of underwater listening devices to track submarines. Instead of enemy engines, they often heard the Earth itself. They heard the distinct popcorn sound of lava interacting with water. They heard the harmonic tremors of magma moving through underground pipes, like a pipe organ played by a giant. They heard the grinding roar of landslides as seamounts collapsed. One of the most famous sounds ever recorded was a low-frequency noise detected in 1997, nicknamed the bloop. It was so loud that it was heard by sensors 5,000 kilometers apart. For years, it fueled imaginations, with people dreaming of colossal beasts waking up in the deep. The sound had a biological quality to it, a rising frequency that mimicked the call of a living thing. But the ocean is a place of physical giants as well as biological ones. Years later, careful analysis revealed that the sound was consistent with a massive ice quake, a large iceberg cracking and fracturing off the coast of Antarctica. The Earth moves, and the ocean amplifies its groans. The sounds of a volcanic eruption underwater are distinct from those on land. On land, the gas escapes with a hiss or a boom. Underwater, The pressure suppresses the gas, forcing it to vibrate the water itself. A major eruption can create a continuous, low roar that lasts for weeks. It is a background static to the lives of the whales and fish. Some biologists speculate that marine animals might use these sounds as navigational beacons. A whale migrating across a featureless ocean might listen for the familiar rumble of a specific volcanic ridge, using the geologic soundscape to find its way home. Not all underwater eruptions are explosive. Some are effusive, meaning the lava flows out quietly, like toothpaste. But even these quiet eruptions have a sound. As the lava cools and cracks, it creates a sound like breaking glass or grinding gravel. It is a sharp, crisp noise that carries for miles. When a submarine robot approaches an active flow, the first indication is often not the sight of the glow, but the sound of the crunching rock transmitted through the water to the pilot's headset. But when the eruption is shallow enough, the ocean cannot contain the energy. The water flashes to steam, expanding 1,600 times in volume. This explosion shreds the molten rock into millions of tiny, frothy pieces. These pieces cool instantly, trapping the gas bubbles inside. The result is pumice, a rock so full of air that it floats. After a shallow underwater eruption, the ocean surface can be covered in vast rafts of floating stone. In 2012, a volcano named Havre Seamount erupted near New Zealand. It was a deep eruption, but it was powerful enough to send a raft of pumice to the surface that covered hundreds of square kilometers. It looked like a new island had formed, but it was a floating phantom. The raft drifted on the waves, carrying with it barnacles, crabs, and corals that had attached themselves to the stones. These floating rock rafts are nature's cargo ships, ferrying coastal species across the deep ocean barriers to colonize new islands. A crab might start its life on a beach in Tonga and end it on a reef in Fiji, having surfed there on a stone born from a volcano. These pumice rafts can drift for years. Sailors throughout history have reported sailing through seas of stone, where the water was clogged with grey rocks clinking against the hull. The sound of a ship pushing through pumice is a dry, hissing whisper, a strange friction in the open water. Eventually, the rocks become waterlogged and sink, raining down onto the seafloor far from where they were born, confusing future geologists who find volcanic rocks in the middle of a sedimentary plain. The chemistry of the ocean is inextricably linked to these volcanoes. The carbon dioxide they release does not just bubble up to the surface. Much of it dissolves in the water. This creates carbonic acid. In the immediate vicinity of a vent, the water can be incredibly acidic. In 2004, scientists at the Ifuku volcano watched as bubbles of liquid carbon dioxide rose from the sea floor. They were sticky, coating the camera lens of the robot. The flatfish swimming nearby had adapted to this harsh environment, their bodies seemingly unfazed by the acid bath. These naturally acidic zones serve as crystal balls for the future of our planet. As human activity pumps more carbon dioxide into the atmosphere, the global ocean is slowly becoming more acidic. By studying the coral reefs and animal communities that live near these volcanic vents, scientists can see how marine life might adapt or fail to adapt to the changing chemistry of the future ocean. In some places, the corals are gone, replaced by beds of seagrass that thrive on the extra carbon. In others, the shells of snails are thinner, dissolved by the water they swim in. The volcano provides a grim but necessary laboratory, a preview of a high-carbon world. But the volcanoes also give back. They are the primary source of many of the rare metals we use today. The fluids that rush up from the crust are laden with gold, silver, copper, and zinc. When the black smoke hits the cold water, these metals precipitate out, settling on the seafloor. Over millions of years, this creates massive sulfide deposits. Some of the richest ores on dry land are actually ancient pieces of the ocean floor that were scraped up onto the continents by tectonic collisions. The copper mines of Cyprus, which gave the metal its name, were formed by underwater volcanoes millions of years ago. Today, the ocean floor is sprinkled with these riches. There are nodules of manganese and iron the size of potatoes sitting on the abyssal plains, and massive mounds of gold-rich sulfides around the vents. This has sparked a new gold rush, a race to mine the deep sea. Giant robotic harvesters are being designed to grind up the vent chimneys and suck the ore to the surface. But this comes with a heavy price. The machines would destroy the fragile ecosystems of tube worms and yeti crabs, wiping out species before we have even fully understood them. It is a conflict between the hunger for resources and the need to protect the unknown. The growth of these mineral deposits is agonizingly slow. A manganese nodule grows at a rate of millimeters every million years. It precipitates layer by layer, often forming around a small nucleus, like a shark's tooth or a piece of shell. If you cut one open, you can see the rings, like a tree, a record of the ocean's chemistry, stretching back to the time of the dinosaurs. To pick one up is to hold a piece of physical time, a stone that has sat in the dark, gathering metal from the water, while continents drifted and ice ages came and went above it. This slowness is the heartbeat of the deep. The water in the deep Pacific has been down there for 1,000 years. It sank in the North Atlantic during the Middle Ages, traveled south around Antarctica, and slowly drifted north into the Pacific. It is old water, rich in nutrients, but low in oxygen. When a volcano erupts, it injects a burst of energy into this stagnant system. It is a momentary spark in a very long, slow slumber. There is a rhythm to this activity that is tied to the moon and the sun. Just as the moon pulls the tides of the ocean, it also pulls on the solid crust of the earth. These earth tides cause the seafloor to rise and fall by small amounts every day. While this movement is invisible to us, it changes the pressure on the magma chambers below. Some studies suggest that underwater volcanoes are more likely to erupt during certain phases of the tide, squeezed by the gravitational grip of the moon. The celestial dance of the solar system reaches down into the darkest trench, triggering fires in the deep. The interaction between the rock and the water goes even deeper than the vents. There is a process called serpentinization. It sounds like a word for monsters, and in a way, it creates them. When water penetrates deep into the mantle rocks rich in a mineral called olivine, it reacts chemically. The rock absorbs the water and changes its structure, turning into a green, snake-like stone called serpentinite. This reaction releases heat. It releases hydrogen gas, and it creates a highly alkaline environment. This is not volcanic in the sense of molten lava, but it is a geothermal engine. The hydrogen gas released by this breathing of the rocks can react with carbon to form methane and simple organic molecules. Many scientists believe this specific chemical reaction, rock meets water, is the engine that drove the origin of life. It provides the energy and the building blocks without the need for light. The entire ocean floor is slowly reacting, hydrating, and changing. The planet is like a giant battery, charged by the contact between the ocean and the crust. We often think of the ocean as a bowl holding the water, but the bowl is leaking. Water is constantly being dragged down into the earth at subduction zones and constantly being vented back out at volcanoes. The volume of the oceans is a balance between this input and output. If the volcanoes stopped, or if the subduction sped up, the sea level would change over geological time. The volcanoes are the regulators, the valves that keep the planet wet and habitable. In the deepest trenches, where the old plates are dying, the silence is profound. But even here, life clings to the steep slopes. The Mariana Trench is not just a hole. It is a canyon system grander than anything in Arizona. The walls are made of ancient volcanic rock, now cold and fracturing. At the bottom, 11 kilometers down, the pressure is over 1,000 atmospheres. It is enough to crush the air out of your lungs instantly. Yet, amphipods, small shrimp-like creatures, scuttle across the bottom. They consume the detritus that falls from above, the final resting place of the ocean's waste. Occasionally, a submarine landslide in these trenches creates a turbidity current. This is an underwater avalanche of mud and sand that rushes down the canyon at highway speeds. It can snap underwater internet cables, cutting off communication between continents. It buries everything in its path. These currents are powerful geological agents, carving submarine canyons that rival the river valleys on land. The continental shelf is serrated with these scars, evidence of the violent shedding of the land into the deep. We have explored less of the ocean floor than the surface of the moon, but what we have found challenges our definition of a planet. We tend to think of Earth as a rock with a thin layer of water and life on top. But the underwater volcanoes show us that the rock, the water, and the life are all woven together. The rock gives the water its chemistry. The water melts the rock to make magma. The magma feeds the life. The life becomes part of the rock. It is a continuous churning cycle that happens in the dark, far from our eyes. The isolation of these deep places means that evolution takes strange turns. On isolated seamounts, we find species that exist nowhere else. A specific type of coral, a unique sponge, a fish with a slightly different jaw. They are the Galapagos of the deep, islands of evolution separated not by water, but by depth. The deep ocean is a barrier just as effective as space. A creature adapted to the pressure of 4,000 meters cannot simply swim up and go to another mountain. It is trapped by the physics of its own body. So, each seamount becomes a lonely evolutionary laboratory, drifting through time. And time itself seems to behave differently here. Not in the physics sense of relativity, though gravity is slightly stronger closer to the core, but in the sense of stability. The deep ocean environment is one of the most stable on Earth. Temperatures do not fluctuate with the seasons. Storms do not disturb the bottom. An animal living here experiences a perpetual cold now. This stability allows some deep-sea creatures to live for extraordinary lengths of time. Deep-sea corals can be 4,000 years old. Glass sponges can live for 10,000 years. They are silent sentinels, growing atom by atom, witnessing the slow march of geological time while civilizations rise and fall in the blink of an eye on the surface. This slowness is interrupted only by the violence of the eruption. It is a punctuated equilibrium, long eras of peace broken by sudden, catastrophic fire. A lava flow can pave over a 4,000-year-old coral reef in a day. It is a reminder that nature is both a patient gardener and a careless destroyer. The biology of the deep must be resilient enough to handle both the eternal weight and the sudden end. The gases trapped in these underwater lavas are time capsules. When a rock is brought up from the bottom and cracked open in a lab, it releases gas that has been trapped inside the Earth since the planet formed. Helium-3, a rare isotope, leaks out of the mantle at these volcanic ridges. It is a primordial gas, left over from the solar nebula that formed the Sun. Every time a deep volcano erupts, it is exhaling a breath held for 4.5 billion years. We are sniffing the ghost of the cloud that birthed the solar system. As we move away from the active fires, the ocean floor changes. The lava cools and contracts. The seafloor sinks as it gets older. This sinking creates the vast abyssal plains, the flat, muddy expanses that cover most of the planet. But hidden beneath the mud are the bones of old volcanoes. Seamounts that were once active are now buried up to their necks in sediment. They are the abyssal hills, the most common landform on Earth, yet they are almost entirely covered in dust. They are the rugged texture of the planet's skin, smoothed over by the lotion of time. There are also mysteries of magnetism. As the lava cools, it locks in the strength of the Earth's magnetic field. By studying these ancient magnetic strengths, scientists have discovered that the Earth's magnetic field is not constant. It breathes, growing stronger and weaker over millennia. There are supercrons, periods of millions of years where the field never flipped, and frantic periods where it flipped often. The underwater volcanoes are the tape recorders of this planetary dynamo, storing the data in basalt libraries at the bottom of the sea. Even the water itself is changed by its journey through the hot rocks. When seawater enters the crust, it is stripped of magnesium and sulfate. It loses its saltiness in a way, but gains other elements. The ocean is constantly being filtered through the hot rocks of the mid-ocean ridge. It is estimated that the entire volume of the ocean cycles through the hydrothermal vents every 10 to 20 million years. The ocean is not just sitting in a basin, it is being cooked, distilled, and re-released. It is a processed fluid, chemically maintained by the furnaces below. This chemical exchange is what keeps the ocean's pH stable. Without this interaction with the basalt, the ocean might have become too acidic or too alkaline for life long ago. The volcanoes act as a buffer, a planetary antacid that keeps the chemistry just right for life to exist. It is a delicate balance, maintained not by biology, but by geology. The stone cares for the water, and in this interplay of stone and water, we find the black smokers are not the only vents. There are diffuse flow sites, where warm water shimmers out of cracks over a large area, rather than shooting from a pipe. These are often the gardens of the deep, where the tube worms and mussels cluster in thick mats. The water here is cooler, a gentle bath rather than a scalding jet. It is here that the larvae often settle first, finding a foothold in the warm embrace of the crust before inching closer to the dangerous heat. The danger is real. Submersibles have returned with melted windows, singed by getting too close to the invisible heat. The water pressure suppresses the boiling, so water can be 300 degrees and still look like liquid water. A pilot must trust their senses, not their eyes. To touch the water is to court death. It is a world where the normal warnings of nature, steam, bubbles, fire, are suppressed by the crushing weight of the deep. The danger is silent and invisible, waiting for the careless. Yet, despite the hazard, life clings to the precipice. We have found microbes living inside the pores of the chimney walls, thriving at 121 degrees Celsius. This is the sterilization temperature used in medical autoclaves to kill germs. These organisms, called strain 121, can reproduce in an environment that we use to destroy life. They redefine the upper limits of existence. If life can survive here, inside a boiling rock at the bottom of a crushing ocean, where else might it be hiding? The map of these volcanoes is also a map of the Earth's stress. The ridges are where the tension is released, but there are also transform faults, lateral cracks where the plates slide past each other. These are the sites of massive underwater earthquakes. While they don't always produce lava, they shake the foundations of the ocean. They can trigger submarine avalanches that bury the vents in an instant. The life here exists on a shaky foundation, constantly rebuilding after the ground moves beneath it. And so, the ocean floor is a patchwork of the living and the dead, the hot and the cold. It is a place where the planet is turning itself inside out, revealing its molten heart to the freezing dark. It is a place where the definition of home is stretched to the breaking point, where home is a chimney of poison, a pool of brine, or a raft of floating stone. As we drift further along these ridges, we begin to understand that the surface world is just the attic of the Earth. The basement, the deep, hot, pressurized basement, is where the heavy machinery is kept. It is where the crust is made, where the water is cleaned, and where the oldest forms of life still hold court. It is a world that does not need us, does not know us, and continues its slow, fiery work in the absolute dark. Off the coast of the big island of Hawaii, a new world is waiting to be born. Thousands of meters beneath the waves, a seamount known as Kamaehuakanaloa, formerly called Loihi, is slowly building itself up from the seafloor. It is the youngest volcano in the Hawaiian chain, a chaotic, rumbling infant compared to the ancient weathered peaks of the islands we see today. It is currently about 3,000 feet below the surface, a dark mountain of fresh pillow lavas and hydrothermal vents. Scientists monitoring its activity have recorded thousands of earthquakes shaking its slopes, signaling the movement of magma deep within its core. It is growing, layer by layer, eruption by eruption. But the ocean is deep, and the process is slow. It will likely take another tens of thousands of years before its peak finally breaks the surface of the water, greeting the sun and becoming the next island in the archipelago. Until then, it remains a secret kingdom, a cradle of geological creation hidden in the blue gloom. The summit of Kamaehuakanaloa is a place of collapse and renewal. It has a caldera, a massive sunken crater, similar to the one at Kilauea, but filled with absolute darkness. In 1996, a massive swarm of earthquakes shook the seamount, and a large section of the summit collapsed, creating a new pit crater. When submersibles visited the site later, they found that the old hydrothermal vents were gone, buried under tons of rock, and new ones had sprung up in their place. These new vents were spewing water as hot as 200 degrees Celsius, confirming that the heart of the volcano was still beating strongly. It is a reminder that the geography of the ocean floor is not permanent. It is a fluid, shifting landscape that can change completely in the span of a single human lifetime. While Kamaehuakanaloa is a quiet builder, other underwater volcanoes are capable of violence that shakes the entire planet. In January 2022, the Hunga Tonga Hunga Ha'apai volcano in the South Pacific erupted with a force that stunned the world. Unlike deep-sea eruptions that are suppressed by water pressure, this volcano was sitting in shallow water, the perfect depth for catastrophe. When the magma hit the seawater, it flashed into steam instantly, expanding with explosive power. The blast sent a plume of ash and water vapor 58 kilometers into the atmosphere, touching the edge of space. It was the highest volcanic plume ever recorded, piercing through the stratosphere and into the mesosphere. The energy released by the Tonga eruption was terrifying. It generated an atmospheric shockwave that circled the Earth multiple times, moving at the speed of sound. People in Alaska, thousands of miles away, heard the boom as a distant, cannon-like thud. The pressure wave was so strong it caused ripples in the atmosphere that could be seen from space, looking like a stone dropped into a pond of clouds. But the most significant impact was invisible. The eruption injected roughly 50 million tons of water vapor into the stratosphere. Because water vapor is a potent greenhouse gas, scientists believe this single event may have temporarily warmed the planet, a rare anomaly where a volcano caused warming instead of the usual cooling associated with ash blocking the sun. Underneath the water, the Tonga eruption devastated the local seafloor. Pyroclastic flows, avalanches of hot gas, rock and ash, did not stop at the water's edge. They raced underwater, hugging the seafloor at incredible speeds. These underwater density currents traveled for dozens of kilometers, snapping underwater telecommunications cables like thread. The island nation of Tonga was cut off from the digital world in an instant, plunged into silence by the mountain's rage. These underwater flows scoured the seabed, destroying life and reshaping the topography in a matter of minutes. It showed us that the destructive reach of a volcano does not stop when it hits the ocean. It simply changes form, becoming a heavy, suffocating landslide of boiling mud. We have also discovered volcanoes that act as time machines, producing rocks that haven't been seen on Earth for billions of years. The West Mata volcano, located in the Lau Basin near Fiji, is one of the deepest actively erupting volcanoes ever observed. At a depth of 1,200 meters, it was caught in the act of exploding. A submersible robot filmed bright orange molten bubbles of lava blowing apart as they hit the water, a violent strobe light in the dark. But the lava itself was special. It was boninite, a type of rock that is almost never found in modern eruptions. Boninite is extremely hot and rich in magnesium, and it is usually associated with the very early stages of subduction zones, conditions that were common on the ancient, primitive Earth. By studying West Mata, geologists are essentially watching a rerun of the planet's infancy, seeing how the first crust might have formed in the chaotic oceans of the past. The scale of underwater volcanism can sometimes be so vast that it threatens all life on Earth. In the geological record, we find evidence of large igneous provinces, or lips. These are massive outpourings of lava that cover millions of square kilometers, far larger than any single volcano. The Ontong Java Plateau in the Pacific Ocean is the largest of these. Formed about 120 million years ago, it represents a flood of magma so huge it would cover the entire continental United States. This event wasn't just a mountain building. It was a planetary burp of heat and chemicals. When these massive underwater floods occur, they release enormous amounts of chemicals into the ocean. This can lead to an oceanic anoxic event. The excess nutrients trigger massive blooms of algae and plankton on the surface. When these organisms die and sink, the bacteria that decompose them use up all the oxygen in the water. The ocean suffocates. Large sections of the deep sea become dead zones, devoid of oxygen and hostile to complex life. The geological record shows layers of black shale from these time periods, the dark, organic-rich mud of a stagnant, dying ocean. These events are often linked to mass extinctions, silent apocalypses, where the breath of the volcano choked the life out of the sea. But volcanism is not just a tropical phenomenon. It happens under the ice caps as well. The Gakkel Ridge runs beneath the Arctic Ocean, separating the North American and Eurasian tectonic plates. It is the slowest spreading ridge on Earth, moving apart at less than a centimeter per year. For a long time, scientists thought it would be geologically dead, too cold and slow to produce much magma. But when they sent nuclear submarines and icebreakers to map it, they found the opposite. The ridge is alive with explosive volcanism. In 1999, seismometers detected a massive swarm of earthquakes along the Gakkel Ridge. When researchers returned to the site, they found evidence of a massive explosion that had happened miles beneath the sea ice. The pressure at that depth, 4,000 meters, should have prevented an explosive eruption. The fact that it exploded anyway suggests the magma was incredibly rich in gas, essentially a carbonated eruption under the polar cap. The robots sent down to investigate found vast carpets of yellow sulfur-rich microbial mats growing on the fresh lava, a secret garden blooming in the coldest, most inaccessible ocean on Earth. This interaction between ice and fire creates unique acoustic environments. When an underwater volcano erupts in the Arctic, the sound waves are trapped between the seafloor and the ice cover. The ocean becomes a reverberating chamber, the noise bouncing back and forth, traveling for huge distances. It is a noisy, cracking, rumbling world beneath the silence of the snow. The dangers of underwater volcanoes are not always from the fire, but from the fall. The slopes of these submerged mountains are often unstable. They are built of loose rubble and slippery glass. Over time, gravity takes its toll. Massive sections of a volcano can simply shear off and slide into the abyss. The Storegga slide, which happened off the coast of Norway about 8,000 years ago, was one such event. An area of the continental shelf the size of Scotland collapsed and slid into the deep. This underwater landslide displaced so much water that it created a tsunami that devastated the coastlines of the North Atlantic. Waves 20 meters high crashed into Scotland and the Faroe Islands, wiping out Stone Age settlements. It was a silent disaster, triggered perhaps by a small earthquake or the release of methane gas destabilizing the mud. Today, scientists map the scars of these ancient slides to understand where the next one might happen. The Canary Islands and Hawaii are both scarred by ancient landslides, reminders that the mountains we see as solid are actually slowly crumbling into the sea. As we look deeper into the relationship between water and volcanoes, we begin to see that Earth is not unique. The conditions we find at the bottom of our ocean, heat, water, darkness, and chemical energy, are likely duplicated elsewhere in our solar system. The most promising candidate is Enceladus, a small, icy moon of Saturn. Enceladus is covered in a shell of bright white ice, but beneath that crust lies a global ocean of liquid water. In 2005, the Cassini spacecraft discovered plumes of water vapor and ice particles shooting out of cracks in Enceladus's south pole. The moon was erupting into space. Cassini flew through these plumes and tasted the spray. It found salts, organic molecules, and most importantly, tiny grains of silica. On Earth, silica grains of that specific size and shape only form in one place, inside hydrothermal vents where hot, mineral-rich water meets cold ocean water. This was the smoking gun. Enceladus has active volcanoes on its seafloor. The implications are staggering. Enceladus is a tiny moon, far from the sun, yet it has the three ingredients necessary for life: liquid water, organic chemicals, and a source of energy. The floor of that alien ocean is likely dotted with chimneys similar to the ones we find in the Atlantic and Pacific. In the pitch blackness beneath the ice of Saturn's moon, there could be ecosystems clinging to the warmth, completely unaware of the universe above them. They would be life forms powered by tidal friction and planetary heat, thriving in a place that looks dead from the outside. Jupiter's moon Europa is another water world. It is larger than Enceladus, with an ocean that contains more water than all of Earth's oceans combined. The surface of Europa is crisscrossed with red-brown streaks and regions called chaos terrain, where the ice looks like it has been broken apart and refrozen, like a jigsaw puzzle jumbled by a giant hand. Scientists believe this chaos is caused by heat rising from below, perhaps from massive volcanic plumes warming the water and cracking the ice shell. Future missions, like the Europa Clipper, are designed to study this moon closer than ever before. We are building submarines in our minds, robots capable of melting through kilometers of ice to swim in an alien sea. We test these robots in the hydrothermal vents of Earth, in the acidic pools of our own volcanoes, training them to recognize the signatures of life. The deep ocean of Earth is the training ground for the greatest adventure in human history, the search for life beyond our planet. The connection between volcanoes and life may be even deeper than we think. Some theories suggest that the prebiotic soup, the mixture of chemicals that gave rise to the first living cells, did not form in a tide pool, but in the pores of a hydrothermal vent. The microscopic honeycomb structure of the rock provided a safe container for the molecules. The heat provided the energy to fuse them together. The flow of water provided a constant supply of ingredients. We may be the children of the volcano, born in the dark, forged in the heat, and only later migrating to the sunlit surface. If this is true, then life is not a lucky accident of sunlight, but a natural consequence of planetary geology. Wherever you have a rocky planet with water and internal heat, you might have life. The universe could be teeming with biological communities huddled around underwater fires, hidden beneath shells of ice or rock, waiting to be discovered. Back on Earth, our relationship with these deep volcanoes is entering a new phase. We are no longer just explorers, we are becoming exploiters. The seafloor is littered with polymetallic nodules, rocks rich in manganese, nickel, cobalt, and rare earth elements, the very materials we need to build batteries for electric cars and wind turbines. The deep-sea mining industry is poised to send massive crawler machines down to the abyssal plains to harvest these rocks. This creates a profound ethical dilemma. To save the atmosphere from carbon emissions, we may have to destroy the seafloor. The mining machines would churn up clouds of sediment that could smother the delicate filter feeders of the deep. They would destroy the hard surfaces that ancient corals need to grow on. We are standing at a crossroads, deciding whether to sacrifice the dark, unseen wilderness of the ocean floor to power our green revolution on the surface. It is a choice that requires us to understand the value of a world we can barely see. The more we learn about underwater volcanoes, the more we realize they are the engine of the planet. They are the reason we have an atmosphere. The gases they released billions of years ago formed the air we breathe today. They are the reason the ocean chemistry is stable. They are the reason the continents move. They are the architects of the world. We live on a thin crust of cold rock, floating on a sea of fire. Every time we drink a glass of water, we are tasting molecules that have cycled through the hot heart of a volcano. Every time we breathe, we are inhaling gases that were once locked in magma. The separation between the human world and the volcanic world is an illusion. We are part of the same system, connected by the flow of heat and matter that has been churning for 4.5 billion years. There is a certain comfort in this deep time. The volcanoes were here long before us, and they will be here long after us. They keep their own time, measured in the slow growth of a manganese nodule or the majestic rise of a seamount. In a world of rushing noise and frantic change, the deep ocean offers a different perspective. It offers the peace of the long view. Imagine drifting down there one last time, past the sunlit waves, past the twilight zone where the whales dive, down into the crushing dark. You float over the mid-Atlantic ridge, seeing the jagged peaks stretching into the gloom. You see the black smoke rising from a chimney, a silent prayer to the geology of the earth. You see a white crab, blind and ancient, picking its way across the rocks. You feel the heat radiating from the ground, the pulse of the planet warming the cold water. It is a world of terrible beauty and quiet power. A world where fire meets water, And instead of destroying each other, they create something new. It is the hidden heartbeat of our home, beating slowly, steadily, in the dark. And as we return to the surface, leaving the pressure and the heat behind, we carry with us the knowledge that the earth is not solid. It is alive, it is moving, it is breathing, and deep down, in the eternal night, the fire is still burning, crafting the future of the planet, one stone at a time. If you enjoyed this deep dive into the hidden fires of our world and want to continue drifting through the mysteries of nature with us, please take a moment to like this video and subscribe to the Sleepy Ocean channel. It helps other weary travelers find their way to our quiet corner of the internet. Let your mind settle, let your breathing slow, and drift gently into the rest you deserve. Good night.